Dalton's Law of Partial Pressure. English scientist John Dalton concluded that the atmosphere is comprised of about 79% nitrogen and 21% oxygen. And in this calculation, we are going to refer to the percentage of carbon dioxide in the atmosphere, and we're going to refer to it as 0.03% carbon dioxide. And we're going to see that when we get to our actual, one of the sample problems that we have. He concluded that the total pressure of a mixture of gases is the sum of the pressures of each of the individual gases. So what he said was, pretty much if we combined all this, right, we were able to get the total gas pressure of the atmosphere. This is called Dalton's Law of Partial Pressures. So, according to his law of partial pressures, if we had two gases and we decide to compress one of the gases, we would be able to combine within this mixture the two gases. Okay? So, Dalton extended this idea about the composition of the atmosphere. If the atmosphere is 79% nitrogen and the atmospheric pressure on a certain day is, right, let's say 101.3 kilopascals, right, standard pressure, then he concluded that the nitrogen itself must be contributing to this pressure. So nitrogen itself, being at 79%, is contributing to that 101.3 kilopascals. So what we have here is, well, 79%, we want to convert that to a decimal, right? So 79%, how do you convert 79% to a decimal? Divided by 100. And then what we're going to do is we're going to take that percentage, so we're finding 79% of this actual pressure. And we get a total of 80 kilopascals. So what we can say is that of this total 101.3 kilopascal pressure that we have in the atmosphere, 80 kilopascals are contributed by the nitrogen gas that's actually in the atmosphere. The other gases in the atmosphere contribute pressures corresponding to their percentage of the total composition of air. So the generalized form of Dalton's law of partial pressure is as follows, that the entire total of the pressure is equal to, you take the pressure of one gas, add it to the pressure of another, add it to a pressure to the other, of another, until however many pressures you have that are of the different gases that are being exerted within that total pressure system. So let's look at a sample problem. What is the pressure contribution of carbon dioxide to the atmospheric pressure on a very dry day when the barometer reading is 0.98 atmospheres? Convert your answer into 3 different units. So let's take that 3% as we said, and we want to convert 3% because 0.3. Right? We know that 0.03% of the atmosphere is made up of carbon dioxide. So what we want to do is we want to take 0.03, we want to divide it by 100, right? Because whenever you have a percentage, get rid of, right? That's elementary math. So, and what we're going to do is we're going to multiply it by the barometric reading of 0.98 atmospheres. Right? So of this 0.98 atmospheres, what percentage or how much of the carbon dioxide is actually active? So what is the pressure of the carbon dioxide itself in the atmosphere? And we get the following number, 0.0000294 atmospheres, which we can write out to 2 significant digits. And we'll put it in scientific notation, 2.9 times 10 to the power of -4 atmospheres. So that is the pressure of just the carbon dioxide in the atmosphere. So what we're going to do is we are going to take that answer, and actually I'm going to take this number because we don't want to take one answer and make the conversion based on our rounded off answer. So I'm going to take the original answer that I got. And we get 0.0000294 atmospheres. And we're going to convert it into kilopascals. So we've got atmospheres. We want to get rid of atmospheres to convert it into kilopascals. And between these two, we know that they're in one atmosphere. One atmosphere is equivalent to 101.3 kilopascals. And when we multiply the two together, we've got atmospheres that cancel out. Our answer will be in kilopascals, and our answer will be 0.0297822 kilopascals. But again, we want to keep to the two significant digits, so it becomes 0.03. Right? The 29 becomes 30, the 29 becomes 30 because of the 7, but we keep an extra 0 to show two significant digits. So there is this answer from atmospheres into kilopascals. And we're going to convert it into one more a different set of units. So we've converted it first into, kept it in atmospheres, into kilopascals, and let's convert it into torr. So we've got 0.0000294 atmospheres. All right. We want to cancel atmospheres, so with formula units, when you're wanting to cancel out, we have atmospheres here, we want to cancel that. So we always multiply by a fraction, and we put that unit in the denominator of our fraction. And we're converting atmospheres, let's say, to torr. We know that in one atmosphere it's equivalent to 760 torr. So if we multiply these two together, our answer will be 0.22344 torr. And again, we want two significant digits, so the answer is 0.22 torr. So therefore, the pressure that's being exerted by the carbon dioxide in the atmosphere is the following, or are the following: 0.22 torr, 0.030 kilopascals, or 0.00029 atmospheres, or 2.9 times 10 to the power of -4 atmospheres. Okay. Gases and natural phenomena. Gases under pressure are responsible for natural phenomena such as volcanoes and geysers. On March 20th, 1980, residents in the northern part of Washington state were told that the rumble they heard from the mountains was a minor earthquake. Deep inside one of the mountains, Earth's crust was moving. The lower portion of the crust was melting into hot liquid called magma. The magma started rising up through cracks in the crust. Trapped water quickly turned into superheated steam, where the trapped gases added to the increasing pressure inside the mountains, which finally, on May 18th, 1980, the top half of Mount St. Helens blew away into a gigantic explosion, releasing all the built-up pressure, along with many tons of rock and ash, 20 kilometers into the atmosphere. So notice here we've got the increase in pressure and just the kind of damage that it can actually do. So being able to understand the properties of gases will help us understand these kind of events. Now, in the end, it released steam and gases such as carbon dioxide, nitrogen, sulfur dioxide. So it released other types of gases. Remember, all those combined together, right, form the total pressure, right? Looking at Dalton's law of partial pressure.